as was mentioned, today I'm going to talk. Today I'm going to talk about simpler and tighter DI security proofs. This is a merging of two works. The first is about a generalized Renner entropy accumulation theorem, and the second work is about how to use this EAT in a device-independent setting. In total, I worked together with Amir Kant, Ernest Hahn, and Peter Brown. Okay, so the broad structure of today's talk is, first I'll talk about the Renner EAT, and then I'll talk a little bit about Petz-Renner divergences and how one can use them in the DI setting, and then I'll conclude. So first, I want to talk about what entropy accumulation theorems actually want to show. So for that, I need EAT channels, and then I'll talk about our results. Basically, at a very big picture, you can think of some bipartite state. Half of this state gets sent to an adversary. This is their quantum side information. You keep the other side of the register, and this is what you use to generate random bits. How do you do it? Well, you apply a channel to it. This channel produces two types of data. A is the private data. This is the data you want to use to generate randomness. And then the other data is public data. This is what at the end of the protocol you'll make public, and Eve will have access to it. And now you keep doing this because you want to generate a lot of random data. So you just sequentially apply a channel, and again, and again, and again. And the question you want to ask is, how random are your private data? Is your private data conditioned on Eve having this quantum side information and the public registers? In other words, we want to ask the question, how do we bound this movement entropy? And also, as was kind of mentioned today in Jan's talk, there's a closely related quantity, namely the up arrow sandwiched in the entropy. So I'll basically switch between them depending on which quantity makes my life easier, but they both kind of quantify the same thing. Of course, I didn't really say anything about the initial state or the channels, so most bounds one can generate on the min entropy are kind of trivial at the end. Basically, from a cryptographic perspective, how do we motivate this? Well, you kind of want to optimize over the input state, but you can kind of imagine there's a lot of channels for which if I can choose the input state, they are not going to produce any randomness, and so you kind of need to add additional constraints. The way this is typically done is via testing. So in addition to producing the outputs, you want to produce some test data, and this data will let you, test data will let you know if basically you're generating randomness or if everything is classical and deterministic. For today, you can kind of imagine the test data taking one of three values. You have 0 and 1. This is basically the test itself. It either fails or it passes the test. And for most rounds, you're not actually going to do a test, so that's represented by this perpendicular sign. Now, then at the end of the protocol, you look at the distribution of the test data, and you say if it lies inside some accepted set, then everything went well, and if it didn't, you throw everything out. So what's known? Well, basically, the following is known. The left-hand side, it's the smoothment entropy of the private data and the test data. The fact that they both are on the left-hand side is a little bit of a quirk of the EAT. Depending on how you look at it, sometimes S is also just projectively reconstructed from the A's and I's, so they don't really contribute anyway. And basically, the main statement is that the entropy that you accumulate over all rounds grows linear in the number of rounds. And then you have some second-order term that's a little bit big and a little bit ugly, so I don't want to write it out. The single-round quantity depends on just a single channel. So what is this channel M? You can kind of think of it as the worst channel that you have here, so the one that would produce the least amount of randomness. And basically, now you have a constraint on the system. You're saying, okay, what's the worst state I can feed into the channel such that the channel itself outputs an accepted test distribution? So now you've managed to reduce the analysis to some single round quantity. However, I said the second order term is kind of negligible. It's not really true for even large numbers of n. So even when n is about 10 to the 7, this term basically dominates. And you still get basically trivial bounds on the system. So you can kind of ask yourself, why do these terms arise, right? Is there something that can be improved here, or is this all kind of intrinsic to the analysis? Well, it turns out a lot of these terms arise because one is using the von Neumann entropy. This is not totally surprising. In some sense, the von Neumann entropy is the right quantity in the asymptotic limit, but if you want to shoehorn it into the finite analysis, then you're just going to accumulate some error terms. So what would the goal want to be? Well, we started off with a Renner entropy. Ideally, you'd like to end with a Renner entropy, and the hope is that this therefore gives better second-order terms. So this is what we do. So the result that we get is very similar in spirit, of course, to the original EAT. You get something that accumulates linearly, and now the only term that remains is some term that depends on the accept condition. This term, of course, also appears in the original EAT somewhere in the second order term. And now, how does this first order term look like? Well, it's a little bit large. To maybe understand it a little better, let's compare it to the original EAT. Here, we have the von Neumann entropy. We've replaced it with the down arrow sandwiched in the entropy of a single round. The main difference you could say is that here, the state is constrained on some output distribution. In our case, we don't have that. Sigma can produce any distribution, which we denote by P of S. But the first term, in some sense, constrains it. Q here are the set of accepted distributions. If Q is close to P, or rather if P is close to Q, the first term is 0. But as it diverges, this becomes a penalty term and basically forces that the minimum distribution that's achieved by sigma is close to Q. So this is the equivalent to the original constraint here. And because, as I said before, most test rounds actually aren't testing anything, the distribution of the non-test rounds is going to be close to 1. So you basically imagine this as some prefactor that's basically 1. So you get the original picture, but now you have the Renner entropy instead of a von Neumann entropy. Some points I want to highlight. First of all, the second order term, or the purely second order term here, is much simpler. Here you have some really complicated terms that you'd need to calculate. Also, for those that know a little bit about entropy accumulation theorems, this is actually not what's stated. There are some min trade-off functions included that you have to calculate. This is a little bit of an annoying task. Our bound does not have it at the end. So this generally is the Renner entropy of a single round. No more mention of min trade-off functions. Also, it's convex in the variables, so that basically means in most settings you want to use it. This just reduces to some convex optimization problem that Python or MATLAB can solve, which is quite nice. So let's look a little bit under the hood. Basically what we need are so-called QES entropies. You might have heard them under a different name. So this work by Sang-Fu and Knill are basically calling them QEF entropies. They're slightly different, but in spirit the same. The work by Van Himbeck and Peter Brown, they call them F-weighted Renner entropies. So they all quantify the same thing. They're given in this form. So they depend on some initial quantum classical state and on some function f. Basically, the quantum state is on 3 registers. Here, Q and Q prime are quantum, and S is classical. If you ignore the function f for a second, then the term you basically have is just the normal sandwiched in the entropy condition on classical side information. And now you're just subtracting some function f from these registers. Basically, if f is very small, i.e. if it's a lower bound, then these terms are positive, and essentially this term in total will be positive. However, if f is very large, then this term dominates, and the whole thing will end up being negative. This already kind of leads to the intuition that f, if this whole term is positive, then f is a lower bound on the Renner entropy, and this is the spirit of this slide. So we say f lower bounds the Renner entropy exactly if the QES entropy is non-negative. And this intuition can be taken really far, actually. Basically, f just replaces the usual notion of a min trade-off function, and you can really see it if we kind of consider the following chain of inequalities. I said that this is the entropy 1 to lower bound. Of course, one way of lower bounding it is going from the up arrow quantity to the down arrow quantity, and then just moving the test data to the conditioning register. Kind of want to highlight, due to proof reasons, going from up arrow to down arrow is necessary, sadly, but moving the test data to the conditional register is not necessary. You can do the proof, get tighter bounds without doing this, but I won't talk about that in this talk. So as I said, now we remain with this quantity, and basically what's happening is that for every round that you see the test data S, you can basically lower bound the entropy accumulated during that round by the function f of s. So now what's a lower bound on the entire entropy? Well, it's f of s times the number s occurred during your experiment, and then you sum up overall possible values of s. Maybe more compactly written, this is just f times q, where q is the distribution of s, and f is a vector that contains all of the elements f of s. And then it's just times n, where n is the number of rounds. Of course, you don't really care what the distribution of s is. You only care that it lies in some set, so you take the worst case value. And because we're conditioning on some accept condition, you always accumulate this extra term. The main part of our paper was basically that here you want to optimize for the best f. In some sense, you want to get the best min trade-off function. That's the one that gives you the best lower bound on the sandwich linear entropy. And it turns out that you can actually find it. So that's why there's no more reason to talk about min trade-off functions, because you can basically find the correct one. And what happens is that if you choose the correct one, then the term f times q reduces to the quantity I talked about in the beginning. The only difference is here you have a sum over all different s. To retrieve the thing I gave at the beginning, you remove all of the ones that aren't perpendicular, and then you take the worst case value for this q. And this is how you retrieve the single round quantity I talked about at the beginning. Okay, so this is what I wanted to mention about the linearity. Let's now talk for a second about Petz-Renyi divergences. Here, I want to show that one can actually bound them using a variational approach, and then I want to show how this is actually useful when combining it with the Renyi EAT. So most of you probably already know the Petz-Renyi divergence, and if not, have seen it during one of these talks. So whenever rho is normalized and sigma is some positive semi-definite operator, then it's just given by this expression trace of rho alpha, sigma to the power of 1 minus alpha, and then you take the log and some prefactor. Basically, there are two ways of achieving an upper bound of this as a variational approach. So one is genuinely new, and the other was already kind of mentioned in the paper by Peter Brown, Hamza, and Omar Fauzi, and the DI lower bounds on the von Neumann entropy. They are different. One of them is a little bit annoying to work with in a general DI setting because it has some weaknesses, but they both in principle achieve this bound. So here, the thing you should notice is that rho and sigma no longer have any exponents attached to them, and p and q are polynomials of some matrices z. And the m here just denotes some hierarchy that as m goes to infinity, this approximation becomes tight. So why do we care about the structure to begin with? Well, first of all, the upper bounds on the Renyi divergence provide lower bounds on Renyi entropies. So that's already very helpful. And second of all, it's known that structures of this form are suitable for the MPA hierarchy. That means in a DI setting, bounds of this form allow you to provide lower bounds in a DI setting on the Renyi entropies themselves. So this is what you need to work in a DI setting. Now some additional properties, and this is the main difference between the two approaches, is that P and Q themselves can have very nice properties. So in particular, the nicest property that they will have is that when alpha is between 0 and 1, they can be chosen to be positive semi-definite, and when alpha is between 1 and 2, up to some constant factor, the terms P and Q will also be negative semi-definite. So these aren't just some mathematical properties, they're actually quite useful, especially in the regime where alpha is between 0 and 1. Here, this is something that most people kind of ignore, but in principle, in this regime, the support of rho doesn't actually need to be in the support of sigma. And so what will happen is that one of the variational bounds will diverge if this is not the case. But for the case where this is positive semi-definite, you actually get reasonable lower bounds on this quantity. And this has some applications in advantage distillation. So it really has some uses. And also, but this is more of a conjecture, I think that this property might also be useful for providing lower bounds on a closely related Renyi entropy, namely the up arrow Petz Renyi entropy. So it might be useful there as well. Okay, let's return to the task at hand. We said we wanted to lower bound this quantity. For those that have been paying attention, I've been calling this the sandwich Renyi entropy, but then in the second half, I talked about the Petz Renyi entropy. So in order to make everything work, we lower bound the first by the second. This always works. And now this is the quantity we want to lower bound. So let's consider a specific QKD setup. This is the most standard one. So we have two parties, Alice and Bob. They have some device. They feed an input into the device, and they get outputs. So here, the private data is Alice's output. For those wondering why there's this asymmetry, basically for most QKD protocols, you want Alice to generate a random output, and then you want Bob to reconstruct Alice's output. So only Alice's output really needs to be random, and then the goal for Bob is just to get it. Here, the public data are the inputs. This is what Alice and Bob will communicate at the end of the protocol. And because I also said that they're test rounds, that also means that you need an additional bit that tells you whether or not it was a test round. Just for clarification, the symbol sperp is equivalent to saying that there's not a test round, i.e. t equals 0. And for the simplest case, t equals 0 implies that Alice's measurement input is just x equals 0. And the test that they do, the way that they generate S during a test round, I think most of you probably have seen it. If x times y is the sum of a and b, then everything is good. They say they pass the test, and if it's not the same, then they fail and they output 0. So basically this term here essentially just reduces to how random is Alice's output, given that Alice chose the measurement input x equals 0. In a general setting, basically what you have to do is you have to use the NPA hierarchy to replace the Petz-Renyi entropy basically with a linear function of some mu variables that the NPA hierarchy generates. Also, the distribution that's generated is also just a linear function of these variables, and then the whole problem becomes a convex optimization. Just to see what we got from this, these were basically the best previous bounds you could get from an entropy accumulation theorem, some important data. Here, gamma denotes the probability of a test round. That means if gamma is 1 over 100, then 1 every 100 rounds will be a test round. And here for gamma equals 10 to the minus 3, 1 in every 1,000 rounds will be a test round. The accept condition is whenever they do a test round, they should pass with approximately 80%. And here, the main point I want to show you guys is that even at 10 to the 7, you have a lower bound on the total accumulated entropy of basically nothing. So here you really notice only at this point do you start accumulating, and if you reduce the number of test rounds, then it's even pushed to the right by an order of magnitude. So you really see that you have to do a lot of rounds before you can generate randomness. Now, if you use our approach and you program this, then it improves in this regime especially. So here you get an improvement by about a factor of 3, and it already shows, okay, you can generate much better bounds. I also want to highlight, I just chose the simplest bound to generate this. There's much tighter bounds on the Renner AT that you can program and do better. Here it really was just to show, even if I do the simplest approach, the one that takes the least amount of effort, even that will outperform basically anything you can do with the original EATs. And yeah, so you can see this here. Also for those that were a little bit put off by the NPA hierarchy because you maybe don't use it too often, there actually exist analytic expressions for these Renner entropies for all 4 of the main ones. So the up arrow, down arrow sandwich, up arrow, down arrow pets, and you can just plug that in. So if you want to know a little bit more about this, this was a poster. You can talk to me or you can talk to Abi, who was somewhere in the crowd. I don't see him. And this just makes life a little bit easier if you go down this route. So now I just want to give a little bit of an outlook as to what else we could have done with these techniques and what else needs to be done. So the Renner EAT is not just useful for DI QKD, it's also useful for device-dependent QKD, and also here outperforms the standard methods that are used. And the Petz-Renner divergences, they're also useful for device-independent advantage distillation, but against collective attacks. So here you have basically a condition of security that's related to the pretty good fidelity, and the pretty good fidelity is related to the Petz-Renner divergence, and then you can use the same variational optimization problem. So what can be improved? There's still some things that aren't tight. So one issue is that we start off with an up arrow quantity, a sandwich Renner entropy, and we end up with a down arrow quantity. Ideally, you'd like to end with an up arrow sandwich Renner entropy. However, it's not really known how to do this, but some progress has been done. Jan talked about this. For device-dependent QKD, you actually do end up with the up arrow quantity, and basically the same chain rule was proven in Amira Khan's work with Ernest Tan in the marginal constraint EAT. So this is a step in the right direction, but it's not yet useful for a fully DI security proof. And similarly, I mean, if one generates these improved Renner EATs, then you also want to have the analogous improved numerical tools with it, right? At the moment, we only have them for the down arrow pets, but you'd like them maybe for the up arrow pets. Maybe someone also proves them for the sandwich Renner entropies, but this is a really tough task, and so it still needs to be done. And yeah, that's it. I have extra slides depending on the questions you ask, but otherwise I'll conclude.
questions for Thomas? Yes.
Yeah, very nice talk. So I've got a question. Does the Renner EAT have like the similar Markov condition as
You can
the
do-
original EAT?
I didn't really go into this. You can use the Markov condition. You can use the non-signaling condition. Both work. Both give the bounds you'd accept. So here I was mainly talking about the Markov condition. I just didn't mention it. If you have a non-signaling condition that leads to a difference in the Renner value alpha in exactly the same way as the generalized EAT kind of demands.
Okay, thanks.
Other questions? Yes.
Yes, thank you very much for a nice talk. I have just a brief question about the plot. Is it for which regime of alpha did you, or what is the optimal alpha?
That's a good question. I just kind of asked the computer, give me the best alpha. It's close to 1. It's like 1 plus 10 to the minus 5 order of magnitude.
Okay, but you're using your, like, the bounds for alpha between 1 and 2, right? For the
So because you don't need to actually, right? Like the 1 and 2 is just for the generalized EAT, right? But if you do the normal proof with the Markov conditions, that's good enough for QKD, right? For the AQKD, so you can just do that. But in practice, there's no real difference. So this, like, you anyway, for these values, the best alphas are between 1 and 2. And then the change of alpha values for 1 plus 10 to the minus 5, you're not going to notice. So you could have used either approach, you wouldn't notice the difference. So for all intents and purposes, yes, you could have stayed between 1 and 2. In practice, makes no difference.
Okay, thank you very much.
Another question?
So, thanks for the nice talk. Sort of following up on Garen's question. So then should I really think of it as like all that's being fixed is the second order scaling if I really don't actually care about being that far away from alpha equals 1?
Yeah, I mean, in some sense, it's kind of hard to talk about a scaling for fixed alpha, right? Like the reason you have a second order term and the reason this like alpha over alpha minus 1 is second order is because you choose alpha to go to 1 with a factor of like 1 over square root n, right? So in some sense, I guess you could say our bounds are O of 1, but it wouldn't converge to the von Neumann entropy. Only if you kind of choose alpha to scale in some way would you get the original scaling back. I wouldn't really think of it that way. Just say, like for any n that you pick, for the number of rounds, you just optimize over alpha, and then that's the best you can get.
Right, but so there should be a small enough block length where I actually want an alpha that's far away from 1.
Yes,
like
yes.
1.5. Okay.
Yeah. But like in device-dependent QKD, this is really noticeable. There, you have much larger alphas. Sometimes even it might make sense in some scenarios to choose even alpha close to 2. Like it does happen, right? But there you do order of magnitude 1,000 rounds, 2,000, right? But here it's like 10 to the 7, 10 to the 8. All of a sudden, this kind of already constrains the alpha to be very close to 1.
Okay, yeah, that makes sense. Thank you.
One last question, there is. Okay, if not, then let's thank